So, what are we doing tonight?
I don't know what it's called, but it's like a word problem,
Okay.
and it should be really simple if I just don't get it.
All right. Why don't you go ahead and read it for me, and we'll see if we can solve it.
A gardener has 100 feet of fence and wants to use the fence to make an enclosed garden. How long should the garden be to maximize the area?
Okay. Let's make the length of the fence X, or the garden, and the width Y. Okay? So we know what? We know that there's 100 feet of fence. So 100 equals what?
Perimeter?
Which is what, according to my variables?
X plus Y.
No, that's half the perimeter.
Well, 2x plus 2y.
Okay, so that's equal to 100. And they want to maximize area. So what's the area equal to?
X times y.
Okay. So what we can now do is we can solve that equation for one of the variables, substitute it into that equation, and we will end up with a quadratic. Since we have a quadratic, we know the maximum occurs at the vertex, and we can find out what that is. So that's going to be our strategy. Okay, so let's solve this for y. What's y equal to?
50. No.
It's equal to 50 minus x, I think, right? In other words, if I divide everything by 2 to start with, I get x plus y equals 50, which means y equals 50 minus x. Okay? So now we go up into the function that we're trying to maximize, which is the area function. It's not the perimeter function. The perimeter is fixed. It's 100 feet. There's no changing that. But the area, we got a lot of choices here. So we go into the area function. We leave that as x, and instead of y, we put this. 50 minus x. Okay? So now this is our area function. I'll write it again over here on the right. Notice what that is. That's a quadratic. By the time I get done multiplying it out, I've got area equals 50x minus x squared. Aha! Well, that's a quadratic. It's a parabola. It opens down. That point right there will be the maximum area. In other words, this is area, this is x. So if I graph this quadratic, area equals 50x minus x squared, and then figure out where the vertex occurs, that number right there will be the maximum area you can possibly make. Okay, so let's figure that out. Minus x squared plus 50x is our quadratic. Where's the vertex of that? What's the formula for vertex?
Is it like negative b over 2a or something?
Yes, that's the best one to use. So what is negative b here?
50.
Negative 50, right?
Negative 50.
Okay, and what is 2a?
negative x squared.
It's the coefficient. It's the coefficient of x squared. It's not, it's just like b had nothing to do with x. It was the coefficient of x. Well, a is just the coefficient of x squared, so minus 1. So 2 times minus 1 is minus 2. So this number is equal to 25. So what that says is that when x equals 25, we will have our maximum area. What will it be? Well, y will be 50 minus 25, so y will be 25, or the area is x times y, so this would be 625. In other words, if I plug in 25 for x into the area function, I get 625. So 625 is the maximum area. Now, let's look at this problem. In other words, the answer came out to be a square, 25 by 25. And that's always going to be the answer when you're trying to maximize a geometric shape's area, is the closest thing to a square that you can get. A circle would be even better. Just keep that in mind, that when you're doing math, the maximum occurs when then the shape of the object is as condensed as it can be, and a square is more condensed than a rectangle. A rectangle can be like this. There's no way you're getting the maximum area from that kind of a shape. You're going to get the maximum area from squares or hexagons, stuff that is like a circle. All right, what else you got?
You have 80 feet of fencing to enclose a rectangular region. Find the dimensions of the rectangle that maximize the enclosed area. What is the maximum area?
Isn't this the same problem, only with a different number?
Yeah.
Exactly the same, right? Did I miss something? It's identical, only with the number 80 instead of 100?
Basically.
Yeah. So, what we just figured out, we don't even have to do the math. We know that a square is going to be the maximum area with an 80-foot perimeter. I mean, we could go through the math again if you like, just to refresh you or make sure that you can do it. But shall we do it?
Yeah.
Okay, so what's the perimeter equal?
80.
And what's that equal in terms of a function?
2x plus 2y.
Okay. And what's the area equal to?
X times y.
All right. So, solve that for one of the variables. Doesn't really matter which one.
X equals 40.
What?
X equals 40.
No. In other words, are you going to solve it for x?
Yeah.
You got to get the y on the other side. But first of all, let's reduce it. Let's make it this instead, because this is easier to deal with. So now solve one of the variables.
40 minus y equals x.
Okay. So now we substitute that for that, because we're trying to maximize the area function. So the area is going to be 40 minus y times y, and now I'll let you take it from there. What's that equal?
Equals 40y minus y squared.
Okay. Which is some kind of a parabola that points down. Okay, so we have to figure out what next.
The vertex.
Okay. So the vertex of this quadratic function is?
20.
So it's minus 40 over minus 2, 20, yes. So, and we figured for y. So y is equal to 20, which makes x equal to?
20.
There's our square again. In other words, the shape of that object has to be a square. It's always going to be a square. Okay?
Okay.
What else you got?
A sheet of paper is 10 by 14 inches. Squares are cut out from each corner and the sides are folded up to make an open top box. How big should the square be to maximize the volume?
Okay, make sure you understand what's happening here. This is a classic problem for calculus also. In other words, we're going to cut out these corners, and then we're going to fold it up along that dotted line, fold up those flaps, and we'll end up with an open box without a top on it, right? Okay, let me erase those I just drew that so you knew what they're talking about. So the question is, obviously if I make these really tiny, if I make these squares like that, I'm not going to have a very deep box, am I?
No.
So the volume won't necessarily be big. If I make the squares too big, in other words, if I make the square this big, I won't even have a box because I won't even have any flaps to open up. So too big of squares won't create a lot of volume, and too small squares won't create a big volume box. So we got to have just the right size. And that's why it's a math problem. So where do I want to begin?
Set up an equation.
First of all, let's set up a variable. The best way to solve a word problem is to always start by defining your variables. If you don't start out defining your variables, it's really hard to progress. So what's my variable and what is it?
The squares would be x.
Let's make x the side of each square. So I can label that x, that x, that x, that x, that x, that, and that. Now, what is the volume of my box going to be? What's the formula for the volume of a box?
Length times width times height.
What is my length?
14 minus 2x.
What is my width?
10 minus 2x.
And what is my height of the box?
X.
Exactly. Okay. Now, we want to maximize volume. Well, we have to multiply these together. So let's multiply the x first times that makes that. And then let's FOIL these two together. What do we got? Help me FOIL this together.
140x. minus 28x squared. Minus 20x squared. Plus 2x cubed.
4x cubed.
4x cubed, sorry.
Okay, now let's rearrange it and combine like terms. So we'll put our highest degree in front. Combine those two, we get 48x squared plus 140x. There is our volume function. If we want to maximize that, we want to factor it first. Can I factor anything out of that?
X.
I can factor 4x.
4x.
Yeah, it might make the math a little easier if I factor 4x. That leaves x squared minus 12x plus 35.
Yeah.
So that's the volume of our box. And we're basically going to do the same thing. We're going to analyze that quadratic and figure out where it is at a maximum. Hold on a second. Something's wrong here. What is it? Notice one thing. What is our domain of x? Let's talk about that. What can x be and what can't it be?
It can't be 0. And it can't be more than
Right, because if it was 0, the volume of the box would be 0. And it can't be more, it can't even be 5. Because if it was 5, we also would not get a box. We would just get 2 pieces of paper folded together. So we would have 0 volume. So x domain has to be greater than 0 and less than 5. Okay, so let's keep that in mind. Now, the question is, how do we find the volume of a cubic function, the maximum volume? This thing factors. Does that help? It might help solve it a little bit. Let's see. That's x minus 5 times x minus 7. So I'm looking at let me pull up Wolfram Alpha and graph this. Are you allowed to use calculators on these kind of problems?
I think, yeah, on this one.
4x times x minus 5 times x minus 7. 4x times x minus 5 times x minus 7. Let's see what this thing looks like. It's a cubic, so it's going to look kind of like a cubic function. Okay. Now, notice that there's no absolute maximum to this. In other words, just looking at the function, this is the volume function. Y is the volume, x is the size of the cutout. But notice that we're restricted from 0 to 5 for x. So the maximum has to occur right there. Looks like x equal 2 is a local maximum for that cubic function. And it's the maximum within our domain. And in fact, we need, Let's see, what happens? Yeah, we have to graph this. We don't know how to find the maximum of a cubic function. So graphing this in your calculator is the only way you're going to be able to come up with the answer. And then you need to go into the calculator. Do you know how to do trace and find a maximum?
Yeah, but my calculator is dead. I don't know what's wrong with it or something.
Okay, well, what do you have, a TI-84 normally?
Yeah.
Well, you'd put your function in, y1 equals, you'd get your calculator, your graph up on the screen, hit compute, choose maximum, put it on trace, mark to the left of the maximum that you see there, mark to the right of the maximum, and it'll tell you what that maximum is. It looks from my graph here like 2, but I can't be certain that it's 2. It could be over here a little bit. It might be 1.95 or something. And I don't have that capability on this program here that I can go in and figure out what that is there. So you're going to have to do that on your calculator. Let's see if it really is 2. We can figure out what the volume is when x is 2. Volume is going to be 4 times 2 times a minus 3 times a minus 5. What is that? That's 8 times 15. That's 120. See, it's hard to tell if that's the maximum. In other words, if I go in and put in 1.9, does that make a bigger number than 120? It's a calculus problem, and we can certainly solve it with calculus, but you're not doing calculus yet, right? You're supposed to be able to solve this with pre-calc?
Yeah.
Which means you have to solve it by graphing it.
Yeah.
It's a relatively simple calculus problem. The calculus solution, let me see if it's 2. I get 12x squared minus 96x plus 140 has to equal 0, and you solve that. Yeah, that's not so easy to do. Solve that. So I won't go through the math to do it, since you're not doing calculus anyway. So it's a graphic problem. Calculator problem. But you get the idea. Notice that when you have a cubic, you can't figure out where the maximum is easily. You don't have a vertex of that cubic function. Whereas a quadratic only has one maximum or one minimum. There's no question about it. If I have a quadratic function, well, that's the minimum, or that's the maximum. It's not like a cubic where there's a local, that's called a local maximum, and this is a local minimum. And it just so happens that on our curve, that we know our domain is restricted from 0 to 5, so we only have to find the maximum in that region there. And that comes right about there. But your calculator would tell you what it was. Okay? What else you got?
This is a little different.
Okay.
But it's determine whether each function is even, odd, or neither.
Okay.
So the first one is f of x equals x cubed plus f.
Let's talk about even functions and odd functions.
Yeah, determines even, odd, or neither.
If the test is to see what f of minus x is, if f of minus x is equal to f of x, then it's even. If f of minus x is equal to minus f of x, then it's odd. An example of an even function would be y equal x squared. That's even. Example of an odd function would be y equal x cubed. Well, why is that even? Well, what is f of minus x equal to? If
It would just be x.
same thing, right? So f of minus x is equal to f of x. So that makes it even. Whereas down here, what is f of minus x equal to?
Negative.
Negative x cubed, which is negative f of x.
Mm-hmm.
So these are good functions. You want to probably memorize that. And the reason is that because that's even and that's odd, these two functions are great for this kind of thing. Another even function is cosine, and another odd function is sine. So let's apply that test to this function. So what is f of minus x equal to?
That one would be negative x cubed minus x.
Which, if I factor a negative out, is negative x cubed plus x, which is negative f of x. So that function would be what?
Odd.
Yeah. And if it is neither negative f of x or f of x, then it is neither. Any other result is neither. Got another one?
X squared minus x.
So f of x is x squared minus x.
Mm-hmm.
Okay, what's f of minus x equal to?
Negative x squared. Wait, just x squared. Plus x.
Now, is that f of x?
No.
Is it minus f of x?
Neither.
It's neither. Notice that we were trying to combine an even exponent with an odd exponent. So each of those terms in that function are going to do a different thing. Because that's an even function, that's an odd function. So when you combine an even and an odd, you're generally going to get a neither. Not always, but you really have to put it to the test by checking what f of x is. What else?
X squared minus x fourth.
X squared minus x to the fourth?
Yeah.
What's that going to be?
X squared minus x to the fourth.
Even, odd, or neither?
Even.
Okay. What else?
X squared minus x to the fourth minus 1. Plus 1.
What's f of minus x?
X squared minus x to the fourth minus 1.
Same thing. Also, even functions are symmetrical about the y-axis, like a parabola. In other words, y equal x squared, that's symmetrical about the y-axis because it's even. And odd means it is symmetrical about the origin, not the x-axis, but the origin. In other words, that's y equal x cubed. And there is symmetry about the origin. I didn't draw it very good. Let me see if I can draw it a little better. That's y equal x cubed, which we know to be odd. So you can tell about the symmetry by knowing that that is a reflection about the y and then again about the x. That's what symmetry about the origin means, is that it's reflected over both axes. Okay?
And then the next one is 1/3 x to the 6 minus 3x squared.
Is that going to be even or odd?
Even?
Yeah, we don't even have to do a lot. I mean, we can put it through our test, but we already know that when we have an even exponent, and it's an x, it's a polynomial like this, that doesn't change when we try f of minus x, and neither does that. So f of minus x is going to be f of x.
And then the last one is x square root of 1 minus x squared.
What is it?
X square root 1 minus x squared.
X square root of 1 minus x squared?
Yeah, square root of 1 is over x squared.
So it's x times the square root of 1 minus x squared?
Yeah.
Like that? Okay.
Yeah.
So what is f of minus x?
Minus x over times square root of 1 minus x squared.
Okay. Is that either f of x or minus f of x?
Wait, what?
Is it either? For it to be even or odd, this has to be either f of x, which it isn't, or minus f of x.
Isn't that neither?
Well, that looks to me like minus f of x. In other words, if f of x is this, minus f of x is a minus sign in front of it. And that's what we're looking at. So that is minus f of x, which makes it odd.
Okay.
Notice in this case that we're multiplying. We're not adding. We don't have a polynomial here as much. We're multiplying x to the 1 times this square root of 1 minus x squared. So we can't apply the same rules we were applying when we had a polynomial. We can't just say, well, it's a x squared plus an x to the 4th term. That's clearly going to be even. So when you get them complicated like this, you actually have to do the full analysis. What is f of minus x equal to? And then you have to say, well, try to figure out if that's either equal to minus f of x or f of x. What else are we doing tonight? Besides even and odd.
This is like inverse.
Okay.
So find f inverse of x if f of x equals 2x minus 1 over 6 minus 7x.
Over 6 minus what?
7x.
Like that?
Yeah.
How do you figure inverses?
Well, you switch x and y.
Okay, that's why I wrote y instead of f of x, because that is the first step, is to switch the variables. Then what?
You multiply 6 minus 7x on both sides.
Yeah, in other words, what we're going to do now is solve for y. That's the two steps for finding inverse, is you switch the variables and then you solve for y. That's all you have to remember. Okay, so the first thing I got to do is what you said. That's going to be equal to 2y minus 1. Now what? It gets a little tricky to solve for y here, but we can do it.
Would you subtract? No.
What's the next thing you can do? There doesn't look like there's much left to do here. What can we do now?
The x.
What?
Distribute the x.
Okay. Now here's the key step. What do I want to do next? Remember, I'm trying to solve for y.
Add 1 on both sides.
The concept is we want to get every term that has y in it on one side and every term that has anything else on the other. So you're right, I'm going to add 1 to both sides and I'm going to add 7xy. So my next line is going to be 6x plus 1 equals 2y plus 7xy. With me?
Yeah.
Now, this always is the case with these kind of inverse problems. What's the next step? This is the hardest step of solving these.
Would you divide x on both sides?
Factor out a y
Factor out 1?
from the right side. Notice that's going to give us 2 plus 7x, like that. Now we can solve for y easy. Divide both sides by 2 plus 7x. That's what y is, and that's your inverse. And at this level, these are probably the average degree of difficulty you're going to get on these inverse problems. And they all solve just like this. You have to, in other words, gather all your terms with y and then factor out a y every time almost. Do you have another one?
No, that's the only one I have.
Okay.
And then, these little graphs. Oh, find the domain of the function f of x equals 1 over square root x minus 4.
X what?
Minus 4.
Okay. Domain is about which variable?
X.
Okay. And domain is usually about what x cannot be. In other words, most of the time, x can be anything. If I said this, well, x can be anything. There's no restrictions on it. So the domain for this function would be all real numbers. But this is a little different. There's some things x can't be here because we're taking the square root of it and we're dividing by that thing. So what has to be true about x minus 4?
It cannot equal 0.
It also can't be negative. So it's got to be greater than 0. Because if the whole thing is negative, I'm going to be taking the square root of a negative number. You can't do that. You also can't have the whole thing be 0. So the way you solve this is you take whatever is inside the radical and you make it greater than 0, or if it was just in the numerator all by itself, I would make it greater than or equal to 0. So solve this inequality, what do you get?
X is greater than 4.
That's your answer. That's the domain. Do you need to put it in interval notation?
That's like 4, comma, infinity, right?
Yeah. And it's a parentheses because x cannot be equal to 4. If x could be equal to 4, in other words, let's change the problem so that the problem is this. Now, x minus 4 has to be greater than or equal to 0, which means x would be greater than or equal to 4, and in interval notation, that would turn that into a bracket instead of a parenthesis. Okay? You understand the difference in the two problems? Where it's just in the numerator as opposed to it's the denominator of being divided? That restricts the domain that much more? What other functions do you have for domain? Domain is pretty easy. Range is hard. Domain is easy.
This is a bit different.
Okay.
But it's like a table, and which choices could be possible values of a and b in order to ensure that the relation is not a function?
Okay.
So you have x and then y and 3 and 4. A and 2, 6 and negative 6, 0 and b, and negative 5 and 2.
And the question is, what values of a and b would cause it not to be a function, right?
Yeah.
Okay. What do you think?
Well, for every input, there can only be one output.
Okay.
So
if a was 3, I'd have a problem right off the get-go, right? Yeah, because that means that when x is 3, y is 4 and 2 at the same time. That violates the function rule. It would violate the vertical line rule. In other words, if a was 3, I would have a value there, and I would have a value there. That violates the vertical line rule. So a being 3 would make it not a function all by itself, regardless of b. So there's more than one answer. What did they say? Give an answer for a and b that makes it not a function?
Yeah, there's like 6 different choices.
Okay, what are the choices?
A equals 6, B equals 4, A equals 2, B equals 5, A equals 0, B equals 6, negative 5 equals, A equals negative 5, B equals 4, and then A equals 0, B equals 2.
Let's examine each choice. 6 and 4, is that a function?
No, because there's already a 6 in there.
Okay, so that no function there. About 2 and 5.
That's a function.
Okay. About 0 and 6.
No.
Okay. Because you'd have 2 zeros in the x, and you'd have different values in the y. What about minus 5 and 4?
No.
And 0 and 2?
No.
No, that's still a function.
Yes, this is a function.
In other words, if I put 0 in there and 2 in there, then this point is the same, so I'm not violating any vertical. In other words, I still only have one value for y when x is 0. So the last one doesn't violate, only those three. What else? It's easy to get confused on that last question also, because it's easy to get confused by two y's being the same. In other words, notice that y is 2 there and y is 2 down there, and that's perfectly okay. That does not violate a function. I can draw a function where y is the same. In other words, y is the same there as it is there for two different values of x. That's okay. That does not violate a function. It's when you have two different values of x, or I'm sorry, that you have a value of x that gives you two different values for y. That violates a function.
Okay. I don't really have any more problems.
Okay. Any other questions? We don't have to go all the way to 8. We can stop early if you want. But if you have some questions or you want me to make some up, I'm happy to.
Can you make up some problems about the inverses?
Yeah. That's a good idea to do that. I should have thought of that myself. Find the inverse of that. Why don't you tell me what to write, and I'll write each line.
So x equals y plus 7 over y minus 2. And then you want to solve, well, you multiply y minus 2 on both sides.
So I have x times y minus 2 equals y plus 7. Okay.
So you distribute x, so you get x, y minus 2x equals y plus 7. And then you subtract x, y on both sides. And then you subtract 7 on both sides. And then y is a common variable, so it'll be y minus x.
Not quite. You got to factor a y out from the right side. What do you get when you factor y out? You get 1 minus x. 1 minus x. Now the final step. You see why I get 1 minus x? Whenever you factor something out, always do a check and make sure that if you multiply that back together again, you get this. Well, if I multiply that, I get y minus xy. So it's factored properly. Now the final step is to what?
Divide 1 minus x on both sides.
And there's your answer. Now, you could do one different variation of that answer if you wanted. You could simplify that. Now, not everybody knows this, but A minus B is equal to the negative of B minus A. Always, no matter what A and B are. So 1 minus x I could write as the negative of x minus 1, and the top I can factor out a negative and make it 2x plus 7. Now the negatives cancel. So I end up with a better looking answer because, well, it just is. It doesn't have as many negative signs, and it's got the x in front minus the 1 instead of 1 minus x. So personally, I like this answer a lot better. I don't think you'd lose points if you put this answer on a test. I don't think she could mark that wrong, because there's nothing that says that this is the simplification of that. It isn't. It's just if you notice that. In other words, this is the thing you want to notice. What is this equal to?
Are they equal to each other?
No, it's equal to minus 1. Because the 3 minus x I could write as negative x minus 3 all divided by x minus 3. Now, this comes up periodically when you're, like when they have a quadratic divided by a quadratic, multiplied by a quadratic, divided by another quadratic, and you're supposed to simplify it. So you factor all 4 quadratics and you start canceling. Well, usually you're canceling an x minus 5 over, there's an x minus 5 over here, and they're being multiplied, so you can cancel like that. But you can only cancel same things. Well, this is the one exception. If you have a minus b divided by b minus a, that's always negative 1. So if you ever see that and you're simplifying it, know that that's negative 1. Same thing as x minus y over y minus x. That's also negative 1. All right. Have you had logs and exponents yet?
No.
No, you haven't?
No.
Okay, that's too bad. I was going to give you a good one. Y equal e to the x. Find the inverse of that. Well, you'd switch the variables. Now, how do you solve that for y? Well, you got to take the natural log of both sides. Natural log of x and the natural log of e to the y, that's equal to y. So you got natural log of x equals y. That's the inverse of that. That's why e to the x and natural log of x are such important functions. It's because one is the inverse of the other. Let's see if I can think of any inverse problems that are difficult. Okay, here's one. Y equal x squared. What's the inverse of that?
X equals 1. Would it be square root x equals y?
Plus or minus the square root of x. And that's big because this isn't a function. That's what that looks like. This is the plus side of it. This is the minus side of it. Notice that it fails the vertical line test. Because for a given value of x, there's 2 values of y. The one thing about finding inverses is a function has to be 1-to-1, which means it has to pass the horizontal line test. Notice what y equal x squared looks like. That, right? That is not one-to-one. If it fails the horizontal line test, then it is not a one-to-one function, and its inverse does not exist unless you restrict the function. I can talk about the inverse of this only if I say x has to be greater than 0. Then I'm only talking about half that. I'm talking about that, which is a function, and it is one-to-one, and that's its inverse right there. So, in other words, the inverse, the other thing about inverse is it's always a reflection about the line y equal x. Whenever you're graphing an inverse, you can draw the line y equal x, reflect the function over that line, and whatever you're looking at is the inverse function. So you can talk about inverse functions of functions like this, but only if you restrict the domain. And that's done quite a bit. For instance, they talk about the inverse of sine. Well, the sine function isn't one-to-one. In other words, the sine function looks like, I'm sure you know what it looks like. It looks like this. Forever. Well, that fails the horizontal line test. So that is not a one-to-one function. But they still talk about the inverse sine, which is written like that. But the only way they can talk about the inverse sine is if they restrict the original function to between there and there. In other words, just this part of it here is one-to-one. If I erase the rest of it and only look at from there to there, then it makes sense to talk about the inverse function. But if the function is not one-to-one, then the inverse function doesn't exist. The inverse relationship might, not relationship, it's either a function or a relation. In other words, when I drew that parabola sideways, that is a relation, not a function. Still a parabola, and it still makes a lot of sense mathematically to talk about it, but it's not a function. All right. If you don't have any other questions, we'll call it a session. Okay, all right, Mina, have a good week. I'll talk to you. Let's see, was this this was one you scheduled on your own? Yeah, online. Yeah. Okay, I'll let you do that for the next one, if you like. Okay. I will talk to you next time.
All right.
All right, bye-bye.
Thank you.
You're welcome.